Okay, the question is, what happens to y if x doubles? Now, we can summarize a lot of things we've done regarding these graphs by using this, by answering this question. Okay, now, if y equals x to the p, well, suppose that y equals x to the p, okay? And then suppose that x doubles. Let's let x1 be some value of x, could be any value of x. Double that, x2 is the doubled value of x when x equals x1, okay? Then let's let y2 equal x2 raised to the p. Y equals x to the p, so x2 raised to the p, we're going to call that y2. x1 raised to the p, we're going to call y1. x2 is twice as big as x1. y2 is x2 to the p. y1 is x1 to the p. Well, it follows then that the ratio y2 over y1 is what? It's x2 to the p divided by x1 to the p. And that, by some simple rules that should make sense to you in a deep sense, is equal to the quantity x2 over x1 raised to the p. But of course, what's x2 divided by x1? Well, intuitively, we chose x2 to be twice as big as x1, so x2 over x1 has to equal 2. Now we can show that algebraically, just to be absolutely sure, and double check what our intuition tells us. Pretty much has to be this way, but let's double check it. x2 over x1 is, well, x2 is 2x2, so that's x2 is 2x1, so that's 2x1 divided by x1, and of course we divide x1 into x1, we're left with 2. So algebraically we see very clearly that x2 over x1 has to equal 2 if x2 equals 2x1. Well, what's that mean? Well, it means x2 over x1 to the p is 2 to the p. So y2 over y1 equals x2 over x1 to the p becomes y2 over y1 equals 2 to the p. This tells us then that y changes by the constant factor 2 to the p. And I didn't really complete that statement. Let me write the rest of that statement down there. Okay, again, y changes by constant factor 2 to the p when x doubles. The graph therefore has the characteristic that doubling x results in a y factor of 2 to the p, using the language we've used in this course. Now, an example, let's just let p equal 1.5. Okay, if p equals 1.5, then y equals x to the p becomes y equals x to the 1.5, and you know that x to the 1.5 could also be written x to the 3/2, or even as the square root of x cubed, or if you want, as the cube of the square root of x. Now you should know all those expressions, but this will be the more common way that this is probably going to be expressed. This wouldn't be at all unusual. Okay, well, what's that mean now? What's the implication of what we've done up here? Well, 2 to the p then is 2 to the 3/2. Now we know that y has to change by the constant factor 2 to the p when x doubles. What's that factor for the graph of y equals x to the 1.5? 2 to the p is 2 to the 3/2. That's 2 square root of 2, approximately equal to 2 times 1.414. And I keep stressing a little bit of a few facts. People don't seem to know that the square root of 2 is approximately 1.414. You really should know that. It's just a handy thing to know. It comes up a lot, and you shouldn't always be reaching for your calculator when you want to think about something. That one comes up enough. You're going to think about it often enough that you ought to know that, and you ought to know how big that is compared to x equals 1. Have a visual picture of it. Anyhow, 2 times 1.414 is very approximately 2.8. Of course, the square root of 2 is not a rational number, so you can't write it as a terminating decimal. This is an approximation. And this is enough of an approximation, or an approximation that's appropriate to constructing a graph. It's going to be 2.828, so it's going to be like 2.83. But if you're just constructing a graph by hand, any additional decimal places are not going to be anything that you can judge. You're going to have enough trouble judging 2.8 with some degree of accuracy. Okay, so in any case, here's just one example of a power function, and we want to construct the graph. So I started a graph and I put a point on the graph. Now, of course, we know that for any power function 0, 0, well, not for any power function. For any power function with a positive power, 0, 0 is going to be a point on the graph. And we've seen why that is. Okay, so we want to construct this. Now, here's an x value. Okay, if I double that x value, it's going to come out to here. And what's going to happen to y? It's going to increase by a factor of 2.8. That means if I put a little line here, now these aren't scale markings, these are markings that we use to construct the graph, okay? Put a mark here, I can put a couple of equal marks up here. Right here would be twice as much, right here would be 3 times as much as this y value, and 2.8 times as much would probably be closer to the, obviously closer to the high mark than to the low one. And of course we've got to come out to the x2 value. Okay, so we're going to get a point that lies about here. Our next point, well, we take this value, and that value is about this much. We come up here, we come up here, and this is twice as much as this value. This is 3 times as much. 2.8 times would be about here. Let's say there's about 2.8 times as great. And we're going to double x. So x is going to become twice as big. And here's x. We double it. We come out to about here. So that our point is going to be along this line, and I'm probably not getting these lines very straight because I'm looking at the board from a strange angle, but I want to actually construct this as I'm talking about it. Okay, so again, we've taken this x value, we've doubled and tripled it, and then we've got a factor of 2.8. Now, we know that if we cut this in half, x is going to decrease by a factor of 2.8. So that's going to become just a little bigger than 1/3 is great. We're going to have a point here. And I can't draw any more subdivisions, but if we know if we keep subdividing this, if we keep going halfway, we're going to have to keep going almost 3 times as close to the axis. And that's going to give us a limiting point at 0. So we can safely draw this graph starting at the origin. And there we have it. And that's a pretty good graph of y equals x to the 3/2 if we label it that way. To see how to label this, and I've written this down here, but if x equals 1, then y would have to equal 1 to get this particular function. So all we have to do is pick a point on this graph, any point. Pick a point, any point, and say that, okay, at this point we decree that x equals 1 and y equals 1. So label any point 1, 1. Any point on the curve, of course. So I'm going to pick this point. So x is going to equal 1 here. And y equals 1 here. So right there's a perfectly good graph of y equals x to the 3/2 now. Had I chosen any other point on the graph, it would have been an equally good graph. Now, for this labeling, this distance and this distance, well, this distance is a little bigger than this distance. If we wanted equal scales, then we would have to find the point on the graph where the scales are equal. You might think about that, but perhaps more about that later. Right now, this is a perfectly good labeling. The scales don't have to be equal. There's some advantages to having equal scales, but many times you have a graph where equal scales would just be ridiculous. Okay, well, we could expand our labeling of the axis then. We could label the x equals 1/2 point, where we bring this twice as close to the origin That might put us here. So x equals 0.5 at this point. Y equals 0.5. And that would occur well, let's just see now, relative to some of these other points, just a little above here, or maybe around here someplace. Now, this isn't going to be completely consistent, okay? If this is double this, then the y equals 1/2 point should be a little bit above here, and I'm drawing it a little below because I think my graph is a little bit distorted. And you'd want to try to be consistent, if you understand what I'm talking about there. But right here would be the y equals 0.5, and of course then we could double this 1 and get the y equals 2 point, and we could double the 1 here and get x equals 2. And we could use this graph to make some pretty good estimates of the value of y for a given value of x between 0 and, well, the graph kind of ends here, 0 and about 1.2.